Hi guys. Welcome kind of back here. Um, Let me just pull this up right here, guys. So basically what we're going to be talking about today is ensembles and statistical mechanics. And we're working on a specific one, which is the micro um, conical ensemble. Now, a person that comes to mind here that is given credit for the idea of first coining and defining the word assemble is Josiah Willard Gibbs. Who is Josiah Willard Gibbs? Josiah Willard Gibbs was a professor at Yale um, in the 19th century. He dies around 1905. And he is basically the father of thermodynamics, and he was involved with correspondence with Clerk Maxwell in the 1800s. He really didn't go far from New Haven. He pretty much stayed there, and he worked at Yale all his life. And what's kind of really pretty neat too about Josiah Willard Gibbs is the fact that his father is also well known here in Connecticut, because with the Amistad captives, his father was a professor of ancient languages at Yale. They're buried next to each other in the Grove Street Cemetery. I can actually show you his grave here, so let me just pull this up for a minute here. And so that's Josiah Willard Gibbs's grave in the Grove Street Cemetery there. And I actually kind of tend to go walking over there every weekend, through the cemetery. It's a very peaceful walk. And, and I've taken pictures of Gibbs's grave as well as his father's grave. So let's get on with this. Here we go, guys. So, I thought about how I was going to put this presentation together, and I thought that it was very important for me to start off and define what is an assemble, and then kind of take it from there and do an example of, the air molecules in a room and how that can represent, macro states, but those macro states lead to these um, micro states as well. So we're going to talk in terms of that. So what is an assemble? An assemble is formed when there's a collection of particles. Okay, one particle is called a system, and a collection of these systems is called an assembly. If we have many of these assemblies, we form an ensemble. Okay, so all macroscopically identical members of an ensemble are called the elements. So basically, when we're dealing with a microconical system, our elements are going to be volume, energy, and the number of particles. If we're dealing with a conical system, and let me just pull this down here, we're going to be dealing with number of particles, pressure, and temperature. And when we're dealing with a Gibbs one, let me just go all the way down over here. And we're going up to about here. Sorry guys, I got a little lost there. So it's right around, yeah, the Gibbs conical is going to be that HVT. And that's going to be dealing with the energy, but dealing with the Hamiltonian, the volume, and the temperature. So that's the Gibbs conical. So we have different ways that we can analyze ensembles, but we're going to be basically dealing with the micro conical or NBE one. Now, when I come up to here, so basically, what does that kind of mean? So we can consider the number of particles n. Oh, this is getting into another way of looking at it. But now if we look at the arrangement of the particles and their momentum in a phase state. So basically what we're going to do is we're going to consider basically a room and the molecules that are in the room in equilibrium. And when we do that, we can consider these things called phase states, okay? And these phase states give us what's called the microstates of the molecules that are in equilibrium. So for example, here we might have this microstate here where we have this particular arrangement of molecules in the room. And then we might be over here and we might have this next microstate here. And then finally we might have this microstate UN. Now, so what is the phase space? Well, the phase space corresponds to what we call 6 degrees of freedom. Basically, if we really think about that, we have 3 dimensions in a room because it's like a box. So we have the X, Y, and the Z. So therefore, we would have 3n for position. But these particles are going to have mass and velocity. So being that they have mass and velocity, they have momentum. So there's going to be 3 dimensions for the momentum as well. So that's why we're getting the 6 degrees of freedom here. So between the momentum and the position of the particles. So we can actually just consider a microstate of one particle, which is really pretty cool. So if we did that, we might have this particle, this microstate mu1 here with this one particle here. So we can kind of take a look here, and it looks a little confusing, but you know, we're going to have a momentum in the x direction, a momentum in the y direction, and momentum in the z direction. And then we're going to have these positions, like position, we're going to have a position here, sorry, qx, right? And then we're going to have it in the y and in the z. You know, it just goes to qn here. So basically, if we really think about this here, in order to get the x position, we're really projecting this across the x-axis, across the y, and across the z, in order to determine, you know, momentum and position of the particle. So therefore, with more than one particle, there can be many microstates for the molecules in the room. Now, generally, to analyze this, we would not use a Hamiltonian with time, but we would still use a Hamiltonian. Okay, and what we would get here is we'd get that L of the microstate is going to be equal to the energy. But there is another probability that can occur, that the microstates will have a specific energy E, such that we're dealing with NBE, or that Hamiltonian will not equal E, and in that case, then we'd consider that we'd consider the energy equal to 0, you know, for the Hamiltonian. Now, the probability of finding a specific microstate in our particular room here would be given by this probability right here, where our microstate EV is going to be this here. It's going to be the number of microstates available to the system. Now, if we consider a priori probability distribution, meaning that we're kind of like already got a sense of what the microstates are ahead of time, this will lead us to determining the entropy associated with our room here that we have based on the microstates that we can project that exist in that room. And that's going to be S is equal to Boltzmann's constant times the natural log of the microstates. So kind of what's nice about that is, you know, we can think about in terms of what it means to be a microstate, what it means to have 6 degrees of freedom, okay, in a room. We get a sense of how the molecules are arranging themselves into these particular microstates, and that even just one molecule can form a microstate with 6 degrees of freedom. But there are many molecules in this room. And so we get a way here of analyzing this and figuring out the entropy associated with the system. Now, today, we continue to use microconical NVE to study thermodynamic systems. And one application to the medical field is to use microconical to analyze data in Alzheimer's research. So we don't have a lot of time today, guys, in this video to talk about that, but what I wanted to do is draw your attention to this article here, because this article here deals with the microconical and conical assemblies for MRI brain networks in Alzheimer's disease. It's quite an extensive article, but it gives a lot of information and a lot of pictures, of what they're looking at and stuff as they're beginning to study this, for the Alzheimer's disease. I also included two other sources here. One source that really helped me gain a better understanding of microconical assemblies was this calendar Centennial Library. And I also got some good information here from an overview of microconical and the Grand Canonical Assembly. So guys, that's about it, and I just wanted to introduce that. This topic's been a little difficult for me, but I kind of feel like getting a better grasp of it, and through working through it, and working through the problems that we had that are also very helpful for understanding these microconical systems. So thanks so much, guys. That's about it.